All right, good morning. So we're going to cover the natural exponential function, and I have here the graph of ln x. And if you remember, a couple things about ln x is that we have an intercept on the x-axis at 1. So this is the point 1, 0. In other words, ln of 1 equals 0. That's something to keep in mind. Another thing to keep in mind is that if I say ln of what to give me 1, so where do I have a point something 1? That's this number e, right? So this is e right here. E is approximately 2.718, right? So 2's here, 3's over here somewhere. Not to scale, obviously. Okay, so we need to keep that in mind, all right, for this section. And also notice that this graph passes the horizontal line test. Right? The graph does not, no horizontal line crosses it more than once, which means ln is a one-to-one function, which more importantly means that ln has an inverse function. Okay, and so we're going to define the inverse function of of ln, sorry. The inverse function of f of x equals ln x is exp, okay, exp of x. And this is just the function that undoes ln, okay? So for example, what that means, so some implications, is that if you said this is called the exp of ln x, they undo each other, you just get x. And if you take ln of exp of x, again, you just get x, okay? And that's true for any two inverse functions. When you compose them, they kind of undo each other. Now, because of the points we picked out earlier, what this also means is that if you said, okay, so remember, ln of 1 equals 0. So that means that exp of 0 equals 1. Right? They undo each other. They're inverse functions. And also we said that ln of e is 1, which means that if I take exp of 1, I get the value e. Okay, now what so happens to be the case is that this exp is actually something that we already knew. It's not a new function. It's e to the x power. Okay, and so that's why we call this the natural exponential function. It is the inverse function of ln, of ln x. Okay, which is kind of neat. All right, so this means a lot of things, and we're going to spend some time looking at e to the x power and how they are related, how it and ln are related. Just another note, a Mathematica note here. If you want to say e to the x power in Mathematica, you use the exp function. Okay, and if you see in a textbook where they write exp parentheses, they're talking about e to the x power. It's just another way of expressing it. Okay, now, so the implication here, again, because it's an inverse function of ln, we could say something like this, that e to the x power equals y if and only if ln of y equals x. Okay, so they undo each other again. And if you compose them like we did up here, right? So another way of saying these implications here is that e to the ln x power equals x, and ln of e to the x equals x. Okay, they undo each other again, right? Because they're inverse functions. All right. So let me show you in one way these are very, very useful. And this is really kind of an algebra thing. And in algebra, we don't really approach them exactly like we have here in calculus, but that's okay. The math is still the same, right? So I want to solve this equation. e to the 5 minus 3x power equals 10. All right, so this is a problem for us usually because the variable's in the exponent. But now that we have this logarithm tool and we have these properties of logarithms, this actually becomes a very simple question. This becomes a linear equation. So when I take the ln of both sides, remember ln 10 is a real number. We had a property of logarithms that said if you have a power, the power can come out front as a coefficient. So this is 5 minus 3x times ln e equals ln 10. Okay, now this is actually pretty nice because remember ln e is 1, so I end up with 5 minus 3x times 1 equals ln 10, and now this is just a linear equation. We just solve for x. Okay, so let's see, we have negative 3x equals ln 10 minus 5, so x equals negative 1/3 ln 10 minus 5, which is a real number. Okay, if you plugged it in your calculator, I haven't done this myself, but I believe from the book we can see it's 0.8991, something like that. Okay, makes sense? Okay, now, since we have a function now defined, e to the x, it may make sense to wonder about the graph. So let's go back and look at our graph of ln x. Now, with inverse functions, well, let me draw a new graph so I can show this, okay? An inverse function is a reflection of the graph, something like this. It's a reflection about the line y equals x, right? Because essentially with inverse functions, you're swapping the role of x and y. So remember here, I crossed at 1, 0. All right, so that means my new graph is going to cross or have the point 0, 1. So it's going to have a y-intercept at 1. And you just imagine reflecting this pink line about that axis here, this straight line here, and you get something kind of like this. And this is f of x equals e to the x, right? Where the pink is ln x. Okay, so that's what the graph looks like. So that tells me then I can see a few things. So note here, so here's some properties. One, if I take the limit as x goes to infinity of e to the x, what is happening? As I go to infinity, this thing's going to get incredibly large. It's going to blow up to infinity. Also, if I take the limit going to negative infinity of e to the x, so as I'm going out this direction, I approach 0. I have a horizontal asymptote going out to negative infinity. Okay, now the domain, so what kind of things can I plug in here? I can plug in anything. All right, so negative infinity to positive infinity are all real numbers is my domain. The range, so what kind of y values can I get out of this thing? Well, notice I'm never below the x-axis, right? And I can actually never hit 0 itself. So the range is a soft boundary on 0 up to infinity. 0 to 1, infinity, non-inclusive. Okay, so there is the properties that I needed to know about e to the x. Or some of them anyway. We're going to keep going over some more. All right, so let's take a look then at how you would approach a problem like this. This is example 3 from the text. We want to find the limit as x approaches infinity of e to the 2x over e to the 2x plus 1. Now, expressions like this have a significance that we don't really have to worry about currently. All right, but anyway, so how would you approach this? What is going on with this complicated function as we go out to infinity? Okay, now the trick here, remember when we took limits of polynomials going out to infinity, we always divided by the highest degree, or the term of the highest degree of the denominator. We're going to do something like that now, what I'm going to do is multiply in on the numerator and the denominator a 1 over e to the 2x, like that. Okay, so if I do that, I just very quickly I get e to the 2x over e to the 2x, and the denominator I get e to the 2x over e to the 2x plus 1 over e to the 2x, right, when I distributed everything. Okay, so that simplifies for me then as the limit as x approaches infinity of 1 over 1 plus, let's just say e to the negative 2x. Okay, so this is, or if you want to, maybe it's more helpful to think of this as 1 over e to the 2x. Okay, so as I'm taking the limit going to infinity, what happens to e to the 2x, just e to the 2x itself, as x goes to infinity? As x goes to infinity, we just said, as x goes to infinity, e to the x goes to infinity. So certainly e to the 2x is going to go to infinity as well. So this term is going to infinity, which means that the entire term, this whole term, is going to go to 0. And so because of that, I end up with just simply the value 1. Okay, does that make sense? If you wanted to write it like this, you can. 1 over 1 plus 0, and so we get 1. And again, I hope that makes sense. If you have any questions, you just leave them in the comments. I'd be glad to help there. Okay, now, in dealing with these things, since we're using exponents or variables as exponents, it's good. This is again some more algebra. These are some laws of exponents, and these apply in general to all exponential expressions, including e to the x. So here's some. I'm going to say a to the x plus y power. Remember, is the same thing as saying a to the x times a to the y. Now, if you want to replace a with e, you've got a property of the natural exponential function. If you say a to the x minus y power, that's a to the x over a to the y. All right, so we divide, subtraction turns into division. And 3, if I have a to the x power raised to the y power, that becomes multiplication. Now, that sounds kind of similar to what we said with logarithmic properties? Remember, we said if you take the log of a multiplication expression, you can divide that up as the sum of two logs. If you take the log of a division situation, that's a subtraction of two logarithms, right? These are the same properties, just looking at it from the exponential perspective instead of the logarithmic perspective. Good. Okay, now let's get into some calculus with e to the x. And this is some interesting stuff here. So first, let's look at the derivative. I want to know the derivative of e to the x. Okay, so I know the answer already, and I don't want to tell you quite yet. I want to look at, let's see if we can figure it out. And I'm going to do it this way. Let's let y equal e to the x. Okay, now remember last time we did some kind of logarithmic differentiation on these things. If you remember, finding these weird derivatives by taking the ln on both sides first. And I'm going to do that now. So I'm going to say ln y equals ln e to the x. Okay, and if I do that, ln e to the x, remember, is just simply x, right? Okay, so now when I take the derivative, implicit differentiation, the derivative of ln y is going to be 1 over y times dy dx, which is what we're looking for. We're looking for dy dx. The derivative of x with respect to x is simply 1. So now solving this for dy dx, I get dy dx equals y. But what was y again? Y was e to the x. That's my answer. The derivative of e to the x is e to the x. That's a really weird thing. What that means then is on my graph. Let's see, where's my graph? When I have this graph here, at any point, the tangent line has slope equal to the height at that given moment. Okay, so for example, the tangent line at 0 has slope 1. Okay, it's a really interesting curve here, really interesting property, which makes taking derivatives kind of fun. And of course, let's go ahead and say that if you're taking e to the u, right, that's going to have to be e to the u times its derivative. You still have to apply chain rule there. Okay, so for example, let me pick a good example here. Let's do example 5 from the text. You have, so find y prime if y equals e to the negative 4x sine 5x. Okay. Now I have a product of two functions here. That's a 1 and that's a 2. So when I take the derivative, I'm going to have to use product rule. Okay. So when I take product rule, or when I take the derivative, let's say I have y prime equals first, that's e to the negative 4x, times the derivative of the second. The derivative of sine 5x is what? Cosine 5x times the derivative of what's inside. That's chain rule. So there's 1 d2 plus 2, that's sine 5x, times, this is the thing that's new for us, d1, the derivative of e to the negative 4x. So we said that's going to be, well, what was it? The derivative of e to the u is e to the u times the derivative of the exponent. So that's going to be e to the negative 4x times the derivative of your exponent, which is negative 4, like that. Okay, and so now we can simplify some. Let me think. I can factor out an e to the negative 4x, and then I'm left with 5 cosine 5x minus 4 times sine 5x. And there I have it. All right, does that make sense? The thing you have to keep in mind, again, this is an e to the u du situation. All right, and if you're looking at the product rule, that's 1 d2, 2 d1. And the d1 is what's new to us. We haven't done that before. Okay, so let's look at another example. Example 6. I want to find the absolute max of f of x equals x times e to the negative x. Okay, so this is like a calculus 1 question, but now we have some stuff we couldn't do in cal 1. And the absolute max, I mean, how do you do that? You take the derivative, find your critical points, find where your derivative equals 0, and then just test to see if it's a min or a max using the first or second derivative test. Since it says absolute max, we need the highest of all the local extrema. Let's just take a look. Let's see how we do this. Okay, so the first thing we need to do for sure is take the derivative. So I'm going to find f prime of x. Again, this is going to be a product rule type situation. You have 1 and 2. So the derivative of the first times the derivative of the second. What's the derivative of e to the negative x? It's going to be, all right, it can be confusing at first. Just write it again. Write e to the negative x, and then the derivative of whatever in its exponent. Okay, so that's e to the negative x times negative 1. That's its derivative. Plus the second, which is e to the negative x, times the derivative of the first, which is 1. And we want to solve that guy for 0. All right, so let's do some simplifying. I can take out an e to the negative x, and when I do that, I have, let's see, didn't I have a positive 1 and a minus x equals 0? Okay, so e to the negative x times 1 minus x equals 0. And this looks like a complicated equation, except remember, what was the range of e to the x? 0 and up, but you can never reach 0. All right, e to the negative x is never going to hit 0. All right, so I'm going to put a note over here on the side. E to the negative x is positive for all x in the reals. right? We can never hit 0 with that. So to solve this equation, we only need to consider 1 minus x equals 0, which means x has to be 1. There's my critical point. There's my critical point. Okay, now, is it a min or is it a max? Yeah, that's a good question. So we can draw a number line, put my critical point there. Remember, I'm plugging into f prime. I'm going to pick some test points. What do you want to say? Something smaller than 1. Okay, how about 0? Something bigger than 1. How about 100? And we plug that into my derivative, so we're plugging it into this function here. If I plug in 0, e to the 0 power is 1 times 1 minus 0, I get a positive value, which means that my graph is increasing from negative infinity up to 1. If I plug in the value 100, I get e to the negative 100. I don't know what that is, but it's positive, times 1 minus 100, which is negative 99. I get negative values when I plug it into my derivative, which means that my function is decreasing from 1 onward, okay? So we could say it like this. We're increasing from negative infinity to 1 and decreasing from 1 to infinity. Logic would dictate then that what? Thus, x equals 1 is where my absolute max is. We'll say the location of my absolute maximum. Okay, now if you wanted to know what that value is, just plug it in. So f of 1 equals 1 times e to the negative 1. So 1 over e is my absolute max. Okay, that's the absolute max. Does it make sense? I hope so. I hope it makes sense. Okay, now let's go ahead and look at integration. Can we do the integral of e to the x? The integral of e to the x dx. Well, so let's think antiderivative. What kind of function, once I take its derivative, gives me e to the x? Well, the derivative of e to the x is e to the x, so therefore the integral of e to the x is e to the x. And of course, if I'm doing an indefinite integral, I have to include plus c. And a more general form of that is if you have a u substitution, right, that's e to the u plus c. So that allows me to do something like this. This is example 8. Let's do the integral of x squared e to the x cubed power dx. That looks very, very complicated, but it's actually not that bad. So if I do a u substitution, let's let u be any ideas. If you have an e involved, your u should be the power. Okay, more than likely your u is the power. So I'm going to let u be x cubed, which means du is 3x squared dx, and I almost have that. I have a 1/3 du equals x squared dx. And so now I can rewrite this integral as the integral of 1/3 e to the u du, right? I've replaced x squared dx with the 1/3 du, like that. So there's my 1/3 du, e to the u. I'm ready to integrate now. That's going to be 1/3 e to the u plus c. So I get 1/3 e to the x cubed power plus c. And there's my solution. And, just like we did in Cal 1, if you're not sure about that, take the derivative and see if you get back to where you were. And you should. You should. Okay, good. Let's try one more because I want to do a definite integral. Let's do example 9. This time we're going to find area under the curve. Find the area under the curve, y equals e to the negative 3x. And here we're going from 0 to 1. Okay, so we just need to integrate that. Setting that up, well, I mean, think about what we're asking for. Practically, before we jump to an integral, area under the curve, we're looking at a physical application here, right? But we understand clearly at this point that area under the curve translates directly to what? Integration, right? So area is going to equal the integral from 0 to 1 e to the negative 3x dx. Okay, so we're going to do some scratch work on the side. We're going to say u is negative 3x, so du equals negative 3 dx. So I almost have that. I need a negative 1/3 du. So this is going to be negative 1/3 integral e to the u du. And I'm going to go ahead and set up a table. If x was 0 and 1, what does u become? Well, let's see. If x is 0, u is 0. And if x is 1, u becomes negative 3. So I have to go from, we have to be careful here, 0 to negative 3, which seems backwards, right? But the signs will work out themselves. So here I get negative 1/3. The integral of e to the u is simply e to the u, going from 0 to negative 3. And so I get, let's see, negative 1/3 e to the negative 3 minus e to the 0. And so if you wanted to make it positive, you can. Factor out a negative out of everything. I get positive 1/3. The negative 1 becomes positive 1. And the e to the negative 3 becomes negative e to the third. Okay, so actually, I would accept either one of these answers. I would accept that. I would accept that. They're the same thing. All I did was just, again, I factored out a negative going from the top to the bottom. I factored out a negative. All right, I hope that helps. I hope this makes sense. Okay, so from there, let's look at section 6.4. I'm going to start at the top. And again, I'm going to post these notes for you. And I'll have a link in the video to them. And we're going to start section 6.4 star. And what we're looking at now are more general versions of exponential and logarithmic functions. So general exponential, let's say exponentials and logarithms. Okay, so I already referenced with properties of logarithms something like this, a to the x. Now, you may wonder, why haven't we considered like log base a? Because maybe in another class you did log base 10 or log base 2 or something like that. Well, to be honest, we don't have to consider those others because they are just scalars of what we deal with now. They're just multiples of what we deal with now. So a to the x is actually e to the x. What do I mean by that? Well, think about it like this. Remember that, let's remember this, e to the ln x power equals x, right? Remember that because they, by definition, they are inverse functions of each other. So a could be written as e ln a. And let's raise that to the x power, right? What's e to the ln a power? They undo each other, and you just get a. So a to the x can actually be written as e ln a x. And then properties of exponents say that that's the same thing as saying x ln a. Okay? So a to the x is actually just another way of saying e to the x times some coefficient. Now, what that means then is if I'm going to take the derivative, I can do it. It's just a simple substitution, right? So the derivative of a to the x, I mean, think about it in this term, the derivative of e to the x times ln a, and remember, that's saying the same thing as e to the x times e to the ln a power, okay? Yeah, and so what you get here, well, no, that's not correct. You can't do that. Sorry, I was thinking, um, I got my properties mixed up, right? A to the xy is the same, I'm sorry, what I was thinking is a to the x times y equals a to the x plus y. A to the xy is the same as a to the x to the y power. Sorry about that, made a mistake. But when I take the derivative here, here's what you end up with. A to the x ln a. Okay, and the reason is because you're basically just applying chain rule, right? So look, if I take the derivative of e to the x ln a, what is that? That's e to the x ln a times the derivative of its exponent, which is going to be the derivative of x ln a. And what's the derivative of x ln a? Remember, ln a is a constant. So what's the derivative of 3x? Just 3. So I get back up to ax ln a. All right, so that's my rule. Let me write it again, just to make it clear. The derivative of a to the x is a to the x times ln a, times the coefficient ln a, okay? So let's see here. Let's find an example. So if I said, hey, this is example 2, let's just take the derivative of 10 of the x. Okay, so we're just applying what we've learned. Okay, the derivative of 10 of the x is just 10 of the x times ln 10. That's it. That's all that's to it. Okay, great. Now, the graphs of these exponentials look very similar to the E graph, and we can actually do that. I can actually pull it up. Instead of using Mathematica for this, I think it'd be a little more straightforward if we use Desmos. So just give me a second. I'll pull that up for you. And I'm going to go to desmos.com. Desmos.com is a free graphing calculator online. Okay, so first of all, let's graph f of x equals e to the x power. And there's that, my exponential. Now we're looking at different, what we call bases. So for example, something close to e to the x, how about 2 to the x? All right, the blue line is 2 to the x. So notice it's still this general shape. It's still going to pass through the point 0, 1, but it just kind of has a little bit of a different curvature to it. Let's do something a little bit more drastic. We just did 10 to the x. Let's do that again. Okay, so it kind of has the same idea, but it curves up a little faster. Right, and so these are what exponential curves look like. Let's do 6 to the x, and we're just kind of filling in the picture here, right? If I pick something between 0 and 1, so something smaller than 1, let's do like 1 half to the x power. Well, okay, that's a little different, right? It flipped its role, which makes sense. I mean, think here your variable is an exponent, so as your exponent gets higher, like for example, if x is 2, you get 1/4. If x is 3, you have 1/8. So as x is going to infinity, 1 half to the x power is actually trending to 0. So if I pick stuff that's below, so let's see, we did 10 to the x, let's do 1/10 to the x. So something below 1 but greater than 0, oops, not squared, x. That would be this red graph. Now watch, let me turn off all the exponentials except 10 to the x and 1/10 of the x. Look at that, they're symmetrical. They have a symmetry to them. We could do the same with 1 half x and 2 to the x, right? Why don't we do 1 over e to the x power, and that is the exact mirror image of e to the x. Oh, where is it? Right there. Okay, so hopefully that can get an understanding of these exponential graphs, that as a gets larger, these things are just going to grow faster and faster. It's like a vertical stretch. Okay, great. All right, let's get back to our notes. Just give me a second. Here we go. And thankfully I didn't black out the screen today like I did last time. Now, you may have heard a lot about exponential growth recently, because one area where we see exponential growth, at least for a point of time, is in the spread of a virus. Okay, so if you heard people talking about flattening the curve, viruses actually spread not exactly exponential. They do for a while, but they'll taper out. They spread more along something called a logistic curve. So it looks something kind of like this. It looks exponential for a while, then it hits an inflection point and will taper out at some sort of resource limit. Okay, so that's called a logistic curve. That they are related to exponential curves, and you will study them when you take differential equations. Okay, so we took the derivative of the general exponential. We need the integral of the general exponential. So if I take the integral of a to the x dx, well, we just said, think about it. We said the derivative of a to the x dx is a to the x times ln a. Ln a is a constant, so they only differ by a constant. So, how do you integrate x? You raise the power and you divide by that power. You divide by the power y because it got canceled out with differentiation. The same is true here. The integral of a to the x dx is going to be a to the x over ln a plus c. And I think that makes sense if you're thinking in terms of antiderivatives. If I take the derivative of a to the x over ln a, I get a to the x over ln a times ln a. The ln a's cancel, and I'm just left with a to the x power. Okay, so as an example here, and in the book, this is example 3. If I say, let's go from 0 to 5, and we want to integrate 2 to the x dx. Okay, so we're wanting to find the area under the curve of one of these exponential curves like this, going from 0 to 5. Not a big deal, right? In fact, there's not really a lot to be done here, because we know from our formula, we know that the integral is going to be 2 to the x over ln 2 going from 0 to 5. Okay, so that's going to be, let's take out the ln 2. You get 2 to the 5 minus 2 to the 0. 2 to the 5th power is 32. 2 to the 0 power is 1. Subtracting those, you get 31 over ln 2. There is your area. There's your area. Okay, good. All right, now let's try one more. This is something we've already done, but I like looking at these, so I think it's worth going over again. Let's take the derivative. So find y prime if y equals x to the square root of x power. Okay, x to the square root of x power. So here when you have something weird like this, like an x to the x power, how on earth do you take the derivative of that? You're going to have to use this logarithmic differentiation technique. Okay, so I'm going to let so let's take the derivative, the ln of both sides. We already let y equal x to the square root of x power. Let's take ln of y equals ln x to the root x power. Why is that helpful? Because now I can take out the square root of x out of the denominator, out of the exponent. And now when I take the derivative of both sides, the derivative of ln y with respect to x is 1 over y dy dx. The derivative of square root of x ln x is using power rule. The first times the derivative of the second times the second, or plus the second, which is ln x, times the derivative of the first, which is going to be what? 1/2 x to the negative 2 power. Okay? Now, we're going to have to do a little bit of work to get this cleaned up a little bit. Let's see, we get root x over x, and this is, isn't that ln x over 2 square root of x? Something like that. And so that's 1 over y dy dx equals all that. So then my derivative is going to be y times that nasty expression. And so remember, y was this ln x to the root x power times all that. Should you try to clean this up further? I don't know. I don't know if there's really a lot of benefit in doing that. Okay, now, actually, so that's my first method, the first thing I could try. And that's probably what I would go to. But remember, we could also use this idea that we started out with, that a to the x can be actually written as e to the x ln a power. Let's try doing that first, that substitution. So method 2, this is kind of neat. I'm going to say, okay, let's just recognize that x to the square root of x power is the same thing as e to the what power? Do you remember how to do this? It's e to the ln x, let me try writing that again, ln x root x power. Okay? So now when I take the derivative of e to the ln x root x power, I just get e to the ln x root x power times the derivative of the numerator. And for that, we're going to have to do product rule, but we just did it up here, right? We took the derivative there, so we end up with this expression. You end up with square root of x over x plus ln x over 2 root x. Okay? And remember that e to the ln x root x power, that's the same thing as saying, let me put some parentheses in here, that's saying e to the ln x raised to the square root of x power, and e to the ln x again is x ln x times all this stuff. Okay? And let's see, we think we made a mistake on the first part. Yeah, my y is not ln x root x, it's just simply x root x. All right, so look, we got the same thing both times. I just need to be more careful in my writing. Okay, so x root x times that nasty thing, and there we have it. So recognizing this property that you can write x to the square root of x power as e ln x times root x in the exponent is actually a very useful thing if we think to do it. Okay, now let's look at general logarithms. And I don't think there's really as much to do with general logarithms. But we define them like this. Log base a of x equals y means a to the y power equals x. And when I'm teaching algebra, what I say is, let's think about it in whirlwind. It's a whirlwind. A to that power equals that. Log base a of x equals y. You have this rotating whirlwind idea. All right, now what we see here is that log base e of x is the same thing as ln of x. So when I write ln of x, I'm actually talking about the logarithm base e. Okay, now the graphs are very similar. They just change by a vertical stretch like we did with a to the x. And really, the reason I said earlier you don't need to think about log base a when we have ln is because of this. So we have the change of base formula, and I've had a lot of people ask, why doesn't my calculator have something like log base 2? And some of them do, but most of them don't. Most of them don't have log base 2 or log base 8. Why is that? Because of this. You can take log base a, anything you want, and you can rewrite it as ln x divided by ln a. So again, the log base a is the same thing as ln x, except it's multiplied by a constant. In this case, 1 over ln a. Okay? So if you're trying to do something like this, example 5, I want to find log base 8 of 5. Now, algebraically, we're asking here, remember the whirlwind, 8 to what power gives me 5? 8 to the what power gives me 5? That is a tough situation. That's a tough question. I don't know. But with change of base formula, it's not really even something I have to worry about because log base 8 of 5 is going to be ln 5 over ln 8. I can put both of those in my calculator and I get approximately 0.773976. And it makes sense to me that that's something below 1. Why? Because 8 to the first power is 8. 8 to the 0 power is 1. So I'd expect, right, here's what I'm saying. Here's 0. I'm sorry. Here's 1. That's 8 to the 0. Here's 8 at 8 to the first. So to get to 5, I need to have 8 to some power between 0 and 1. And that's where we get this 0.773976. That's its power. Right? We get that through looking at logarithms. Okay, good. I hope that makes sense. Now, taking the derivatives and the integrals of these things, well, they are ln x times a constant. So wouldn't you expect then that the derivative of log base a of x to be just like a derivative of ln times a constant? And what is the derivative of ln? The derivative of ln x was what? 1 over x. Remember, that's how we defined it. We defined it as the, well, we defined, no, the way we defined ln x was the integral of 1 over x dx, right? So here, the derivative of log base a of x is 1 over x times ln a, right? It's just the same thing. It's 1 over x times the constant 1 over ln a. And we can figure that out using the change of base formula, right? You take the derivative of this ln x over ln a. I mean, that's 1 over x times 1 over ln a. Okay, because ln a is a constant. All right, good. So if I was going to do something, let's see. Yeah, we'll do this one. We'll do example 6. I want to find the derivative of log 10 2 plus sine x. Okay. So this is a log base a of u situation where I'm taking the derivative. Okay. I think I can do this though. So log base 10 of u is going to be 1 over u. So it's going to be 1 over 2 plus sine x times its derivative times 1 over ln 10. So let's go ahead and multiply. Let me do it like this. Let me start over. And let me actually write what I'm saying here. Okay, so the derivative with respect to x, if you have log base a of u, right, it's the same thing. You just have to apply chain rule. That's 1 over u ln a times du dx. Okay, so here that's going to be 1 over ln a is going to be 1 over ln 10, 1 over 2 plus sine x, times the derivative of 2 plus sine x, which is just simply cosine x. So here I get cosine x over ln 10 times 2 plus sine x, and that's it. That's it. It's not, it looks complicated, but it's really not. Now, something I should point out here, log 10 is called common log, and your calculator does have that one. So if you have just log x, that means common log. That's log base 10. We see that a lot. I mean, think about what that would do. Remember, the logs are talking about your powers. So if you go up in common log by 1, you're actually multiplying your value by 10. Okay. Applications of logarithms in the real world. So intensities of earthquakes are measured with a log scale. So when you go up a little bit in the intensity of an earthquake measurement, you're actually multiplying a lot. So they're way stronger. Sound intensity in decibels works the same way, and pH scale is also logarithmic. All right, now let me show you one other expression, or one other way to express E. Okay, so let's revisit E. All right, so if we have f of x to be ln x, then I know that f prime of x equals 1 over x, right? Okay, so that means if I took the derivative, let's let f prime be, or let's let f be ln x. If I take the derivative and plug in 1, and I'm going back to the definition of a derivative, that's the limit as h approaches 0, f of 1 plus h, right, minus f of 1 all over h. Does that look familiar from your test? I was hoping some of you would make the connection that I was talking about the derivative on the test. All right, and actually there's no harm in just replacing the h's with x's, because that's just standing for some sort of dummy variable here. So I'm taking the limit as x approaches 0 of f of 1 plus x minus f of 1. Okay, now this is going somewhere, I promise. What was f again? F was ln, right? So I'm taking now the limit as x approaches 0 of ln of 1 plus x minus ln 1 all over x, okay? And ln 1 is what? 0. So here I get the limit as x approaches 0. I'm going to take out the 1 over x and have ln 1 plus x. All right, so again, what I'm saying is, remember, that's 0. That's a 0 there. Okay, now, also remember that for properties of logarithms, a coefficient can do what? Can be brought in as an exponent. So here I have, this is the limit as x approaches 0 of ln 1 plus x to the 1 over x power, like that. Okay. And I know, remember, this is what f prime of 1 equals. So I know that, well, I could have just, I mean, why did I go this route? I know that f prime of 1 is just 1 over 1, which is 1. So all of this equals 1, right? All of that equals 1. Okay, so this is going somewhere. All right, so now watch this. This is neat. I'm going to change color. So now let's take e, which is e to the 1, right? Which, according to what we just did, is e to this power, limit as x approaches 0, ln 1 plus x to the 1 over x power, okay? And by continuity, I can just say that's the limit as x approaches 0 of e to the ln 1 plus x to the 1 over x power. And once I do that, e raised to the ln of some power cancel each other out, right? So I finally get that e is the same thing as the limit as x approaches 0 of 1 plus x to the 1 over x power. And that's how, if we went the star route, if we hadn't gone the star route, this is where we would have started our conversation. We'd have started with e and then built up to ln. But I wanted to start with ln and build up to e. But here's how another way we could define e. E is the limit as x approaches 0 of 1 plus x to the 1 over x power. And if you wanted to, you could make a substitution. Let's let x be 1 over n. And in that case, you could say, look, as n goes to infinity, you could have 1 plus 1 over n to the n power, and you get e as well. Okay, so these are a new way of defining e, and which is very interesting. I mean, you think we started out by saying ln is just the area of the curve of 1 over x going from 1 up to x to some endpoint, and then from that we saw that the value that made ln equal 1 was this mysterious number e. It was some irrational number, and now we see that actually e in itself has a lot of value to it as well, or a lot of math behind it, that e can actually be written as a limit of this complicated expression, 1 plus x to the 1 over x power as x goes to 0, or the limit as n goes infinity of 1 plus 1 over n to the n power. Okay, and the funny thing is, these show up in a lot of places, in particular financial situations. So if you've ever dealt with compound interest has a formula that looks something kind of like this. E can provide you the upper bound on what you're going to get out of an investment with compound interest. All right, I hope that makes sense. Guys, this is 6-3 star and 6-4 star. We've covered all of it. If you have a question on it, please let me know. I'll be glad to help you. I want to help. Just let me know how I can, okay? And I guess we'll see you next week. We'll continue on with Chapter 6. Have a good day. Have a good weekend.